a joint program between Imperial College London and University of Reading. And we have plenty of PhD projects on the mathematics of planet Earth topic. And I'm going to talk today about well-posedness properties for a stochastic rotating shallow water system, in which stochasticity is of transport type, and which, thank you, has been derived using the so-called SALT approach, that is stochastic advection by Lie transport. Now, I'm not going to go into details related to the approach itself, on the one hand, because it has been presented in details on Monday by one of my colleagues, and on the other hand, because my main focus is not on deriving these models, but on showing that they are well posed. However, I will explain briefly what motivates this approach. Then I will show how the 2D Euler equation looks like with this type of stochasticity, and I will present some results here. And then at the end, I will present the model itself. So you saw on Monday, so the main idea of the SALT approach is that we introduce stochasticity at the level of the Lie derivative of an advected quantity. Think about a nonlinear transport equation, for instance, and if in the deterministic case we investigate the behavior of an advected quantity, say vorticity, along a certain trajectory, in the stochastic case we are going to investigate the behavior of the same advected quantity, but now on a stochastically perturbed trajectory. So the vorticity equation in 2 dimensions looks like this in the Lie form. Where this is the Lie derivative, and it is the dot product between the velocity vector field and the gradient of vorticity. Here, omega is vorticity, the curl of ut. And now, for the stochastic case, we perturb this field by adding a certain type of noise to it. And we obtain now stochastic PDE. Which looks like this. So this is the stochastic part. Now, these parameters, Xi's, you saw a very beautiful picture on Monday. When we predict weather, we basically have a grid like this over the Earth. If in the deterministic case, we had this initial trajectory, in the stochastic equivalent, after we perturb this field, will look maybe something like this. Well, still differentiable. And these parameters, xi, are in some sense related to this difference between the original path and the stochastically perturbed one. Briefly speaking, this is the main idea. Now, the thing is that here, if this is the grid, here, what I have is basically a geophysical process which is active at a scale which is smaller than the scale of the grid. And these are the so-called subgrid scale processes, which are usually unresolved or are parameterized within the model. The aim of SALT is to basically be able to represent this usually missing physics in a better way, and in the same time to preserve the physical properties of the system. So if originally we had conservation of energy, conservation of circulation, and so on, we want that after we add this stochastic term to still have these properties. And also the analytical properties like existence and uniqueness of solutions or continuity with respect to initial conditions have to be at least as good as those of the deterministic system. Now, these are some examples of processes, for instance, which are of this type, which are usually active at a scale which is smaller than the scale of the grid. I have stolen the picture from ECMWF. Okay, so now we have here a result for the 2D stochastic Euler equation, which has been derived using this approach. And you see, this is basically this equation. We have showed that there is well-posedness in the Sobolev space WK2, that is the space of functions which are k times differentiable with their derivatives in L2. So if we start in WK2 with a divergence-free function, which is a very important technical condition, so the fluid is incompressible, then the two-dimensional stochastic Euler vorticity equation given here admits a global pathwise unique solution. Moreover, if K is large enough, then certain Sobolev embedding theorems allow us to conclude that the solution is even classical. And we have this also nice relationship for the two different solutions. Of course, that uniqueness is actually a consequence of this relationship, the one with expectation you can see over there. But, oh, okay, I can use this. But the thing is that we obtain this relationship using sequence of approximations, which is constructed as part of the proof for the existence of the solution. So this is why we show pathwise uniqueness also independently of this relationship. Anyway, the same well-posedness result holds for a slightly larger class of SPDs. I think there was a question on Monday related to this, because the salt approach, unfortunately, does not conserve energy. It conserves circulation. Since it doesn't conserve energy, we can have a dissipation, and we have to control it. And we can control it by adding here a damping term, for instance. But even, and this is what happens numerically. There is some work done for numerics for this equation, and they add a damping term here. Even in this case, the well-posedness result holds, even for a more general function. Okay, there is also the same, not the same, this is for the two-dimensional case. There is a result for the three-dimensional case where the solution is, of course, just local. It has been proven by Christen, Flandoli, and Hall. And the approach we use here is slightly different because we wanted to be able to generalize it to the case of compressible fluids, which I should say is not trivial. So here we have the main model, basically, the viscous stochastic rotating shallow water system. It is compressible now. If we ignore the red part and the extra viscosity terms from here, then what we have on the left-hand side is basically just the classical rotating shallow water system, which, broadly speaking, models the evolution of a fluid flow in a basin like this in a rotating framework. And U is the velocity of the flow. We have denoted this quantity epsilon U plus R with V, so V is also a velocity. Epsilon is the Rossby number, and R is also related to the rotation of the Earth. So both epsilon and R are related to the rotation of the Earth. Now, mathematically, R is just a function which depends only on space. It is basically the potential related to the rotation rate around the vertical direction. Small f here is the Rossby parameter, and z is just a unit vector which points towards, from the center of the Earth, which points away from the center of the Earth, basically. And P, this is the pressure term, where it is the ratio between eta. Eta is the depth, it's h plus b in this picture, minus the bottom topography b over epsilon f, where f is the Froude number. Anyway, so this is the equation for the velocity, and this is the equation for the depth of the fluid. One of the main difficulties comes from the fact that, as I said in the beginning, the fluid is now compressible. Another difficulty comes from the fact that we have an extra stochastic term. We didn't have this term for the Euler equation. This is a summation over J. Actually, this is equal to Vt1 gradient of psi I1 plus Vt2 the gradient of psi I2. However, we do assume that the psi I vector fields are divergence-free, which simplifies a little bit the analysis for the stochastic term for the second case. And in this case, we have a well-Posner's result in W12 this time. The reason why we cannot go to higher order derivatives is, again, the fact that we do not have the divergence of u equal to 0. The fact that for the Euler equation, the fact that divergence of u is equal to 0 and that the fact that we have this relationship between omega and u simplifies technically some things. We could go to higher derivatives if here we add the Laplacian to a higher power. Then we could still have wk2 here. So we start in W12, and we can obtain a strong solution from a probabilistic point of view. We have rewritten in the same space in W12. We have rewritten this equation in a slightly nicer form. So Li is the operator given by the Lie derivative, is the dot product between psi I and the gradient of Vt. And Ai is this sum, the one I talked about before. And the divergence of psi is 0, the divergence of u is not 0. Okay, how do we prove it? Now, the main idea is to basically construct a system, an iterative system, linearized, which is in C infinity, stays in C infinity, it has solutions there, and the corresponding family of solutions, because for each n we have a solution, the corresponding family of solutions converges in a suitable sense to a limit, which we show that satisfies the original equations from the stochastic rotating shallow water model. This is the linearized system we construct. It's given here. And Pt n-1n is defined like this. So we have a truncation, Fr is a truncation function. We have a truncation function in front of the original nonlinearity, because not surprisingly, nonlinearities create problems. First of all, we did linearize here instead of having the dot product between Utn and the gradient of Vtn. We have Utn-1 dot product gradient of Vtn. But we also need a truncation function in front of it because we want to basically have a linear SPD with Lipschitz coefficients so that we know that it has a solution. And we also have a truncation function here in front of the pressure term. And this is the Ito form. The noise as introduced here is in Stratonovich sense, but we transform it in Ito noise and we work with the Ito form of the equation. And after we transform it, the Ito form gives us this second order term here. Okay, and for the second equation, we do the same. We have a truncation in front of this term, and here we have Utn-1 instead of Utn. Now, stochasticity for the second equation seems to be very close to the stochasticity from the Euler equation. Now, given the fact that we added a viscous term, we are able to show that this a priori, I'm sorry, this accolade is not really in the right place. We are able to show these a priori estimates in the W12 norm. And these a priori estimates allow us to show that basically the family of solutions is relatively compact. And therefore, so both equations, linearized and linearized, have a solution, have a unique solution, because we brought them basically to a particular case of some linear SPDs from the book of Rozovsky, which is a classical book on linear SPDs. They have solutions in C infinity. Now, the a priori estimates I've shown you before allow us to say that the corresponding family of solutions is relatively compact, and therefore it converges in distribution to an equation which is not exactly the original equation, but the original equation plus the original equation with a truncation in front of the nonlinear term and in front of the pressure term. And this is a weak probabilistic solution, but there is a Yamada-Yatanaba theorem for the infinite dimensional setting, which says that if we have a weak probabilistic solution and pathwise uniqueness of the solution, of the original, we need here pathwise uniqueness for the solution of the original stochastic rotating shallow water system, not just for the approximating sequence. Given this, we do have a strong solution for the truncated form of the system. And then we show that we can remove the truncation up to a positive stopping time. So the solution is strong and local. Okay, now how we showed that this holds, this relative compactness property holds using a criterion given by Kurtz. And all we have to do basically is to find a family of random variables such that this conditional expectation is smaller than the conditional expectation of that certain family of random variables. This is not too hard. If we use the mild form of the equation, then we just write these differences. So yt will be in the first case vt from the velocity equation, and in the second case ht from the equation for the depth. And in this way, we can construct this family of random variables. And that's it, basically. This is the paper for the Euler equation, and this is the one for the stochastic rotating shallow water equation. Thank you.
Thank you very much for the talk. We have time for question, but go ahead anyway. Yes, there is one question up there.
Hi, you mentioned the paper by T3 on the lake equations.
Yes.
Well, I don't need to see it, but well, I know of this paper because it's related to a sort of quasi-geostrophic model, which is basically 2D Navier-Stokes with damping. Have you maybe looked at it or see if this could be perhaps be used?
Yes, I did. There is this is actually another result in preparation, but I didn't have time to present it properly. So there is, these are basically the Great Lake equations are basically an intermediate model between Euler and the stochastic rotating shallow water system. And they are the equations modeling the evolution of the fluid when here we have a rigid lid. And only, so we have Euler basically, but plus a bottom topography function. And it seems that technically everything goes as in Euler's case. But we have, instead of having the Sobolev space WK2, we now have a weighted Sobolev space. And the weight is given by this function B, which is the bottom topography. So yes, it works for the stochastic form of the Great Lake equations too.
Thank you. Any other question from the audience? Well, yeah, here we go.
Thanks for the nice talk. Is there any advantage of using the Lie derivatives for, like, from an analytical point of view?
If there is any, sorry.
Is there any advantage of using the Lie derivatives for from an analytical point of view?
I really use the Lie derivative explicitly, so technically I don't use the fact that it is a Lie derivative. I use that it is a dot product between u and the gradient of the advected quantity, and I really have to bound each term separately. So I would say no at this point for well-posedness, at least.
Right. Then I would say that since time is up, I would thank all the speakers again. Thank you very much.